All right, good morning, good afternoon, or good evening. Welcome to the 8th Excelero webinar for 2019. This one is about deploying BeeGFS on Elastic NVMe. For this webinar, I have as special guests Jean-François Le Fillâtre, Senior Systems Architect at ThinkParQ, and Sven Breuner, creator of BeeGFS and currently Field CTO at Excelero. Today's interactive best practices webinar focuses on deploying BeeGFS with Elastic NVMe, which enables customers to leverage the full potential of their NVMe storage. Sven and Jeff will also dig into some key use cases. The bulk of the session, though, you will be the stars, as we want to hear as many questions from you as possible, and of course we will answer them. This is how this will work. Everybody, but our speakers will be on mute, but at the bottom of your UI, you should see a Q&A button. Post as many relevant questions as you want. I will present those questions to the speakers when that works, and I will let them answer the questions for everyone. So, Jeff, Sven, the floor is yours.
Thank you, Tom. Hi, everyone. This is Sven. Welcome to the webinar. Let's start with the agenda. Okay, first thing we'll talk about today is why and where, in the context of deploying BeeGFS on NVMe storage, is NVMe storage actually useful? The next thing we'll cover is the hardware elements that are relevant to actually build fast shared NVMe-based storage systems. And on top of that, of course, we'll talk about the software elements to really take advantage of the NVMe devices and the performance that comes with them. For that, we'll cover two simple software packages, NVMesh and BeeGFS. And in the end, we'll bring it all together and see where this gets us. So for starters, why is everyone talking about NVMe storage these days? As you probably know, an NVMe drive provides extremely high throughput. Comparing it to the performance of classic spinning disks, you get the performance and throughput of about 20 spinning disks out of a single NVMe drive already, which means you can easily build a solution that provides tens of gigabytes per second already in very small 2U systems and at a much cheaper price than you would pay for the same performance with spinning disks. So an NVMe drive these days is about 3 times the price of a spinning disk for the same capacity, but provides 20 times the performance. That's why, from a performance perspective, NVMe storage is much more affordable at high speed compared to spinning disks. The other advantage of NVMe drives are the high and predictable IOPS. As most people in the audience probably know, classic spinning disks suffer from the problem of the head seeks. That means for highly concurrent access, they get really slow and unpredictable because the head has to seek around all the time on the spinning platter. And NVMe drives don't suffer from this problem because they are only chips. So for them, it doesn't matter if 2 blocks are accessed sequentially or completely randomly. To put it in numbers, that means a single NVMe drive already provides the IOPS of 1,000 spinning disks, which makes them, of course, ideal for environments that are highly concurrent or have lots of small random accesses. And the third important thing is the latency. NVMe drives, compared again to spinning disks in numbers, have only 1/100th of the latency for access of a classic spinning disk. That means for NVMe drives, we're talking about microseconds, while for spinning disks, we're talking about milliseconds to access a random block on the drive. So this makes the NVMe drives also ideal to deal with lots of small files, for instance. This might already sound too good to be true, so where's the problem? Luckily, there isn't really a problem. It's just some things that you need to be aware of to design really good NVMe storage systems. So one thing to be aware of is that the traditional concept of hardware rate controllers doesn't work anymore at the speed of NVMe drives, which raises the demand for software-defined storage solutions. So in fact, there isn't even really a good internal RAID controller for NVMe drives, and the external RAID controllers that you'll find on the market typically try to put a lot of NVMe drives behind very few controllers, which means the controller immediately becomes the bottleneck and the connection to the controller as well. So you really need to take care of the balance of the components when designing such an NVMe storage system. And we already talked about the second aspect with this, sharing the performance of NVMe drives over the network. This really requires a software toolkit that is optimized to preserve this low latency and high IOPS and high throughput when accessing the drives over the network, so that you can use them for your shared clustered storage. So let's look at which hardware components are important to keep in mind when you're designing a fast NVMe-based storage system. On the one hand, it's the NVMe drives themselves. They come in different flavors, for instance, as PCI cards, but the typically used one for servers is what's called the U.2 form factor, which means it's a hot pluggable drive that looks from the outside similar to a 2.5-inch classic spinning disk. The various flavors for NVMe drives vary in price, throughput, IOPS, and latency, and endurance. The endurance might be the most important part for server drives, and also the consistent IOPS. With the price drops that we saw this year, they have finally become very affordable. Server drive already retails at about 15 cents per gigabyte, which means a 4 terabyte drive is at about $600 these days. The other important thing to keep in mind as we're talking about shared storage here is, of course, the network. 4 NVMe drives already saturate fully a 100 gigabit network link. So to have a good price performance ratio, you will typically want to have more than 100 gigabit NIC per server to have more than 4 drives per server. The other important thing to preserve the low latency and the high IOPS is the type of network that you use. While generally, technically, everything would work with TCP, the problem with TCP is that it is designed for lossy networks and has a rather defensive, I would say, congestion handling. And congestion is a very normal thing for storage servers, because for storage servers, it's typically many clients versus a few servers. So congestion automatically comes from that. And that's why you want to have something like an RDMA-enabled network that's lossless, and where the congestion handling, the very fast congestion handling, is already built in, so that you can quickly recover from congestion and can preserve the low latency even in situations of high concurrency. And the next important thing is then the memory bandwidth. So to move data in and out of a server at very high speed, you want to make sure that you're using at least 6 memory channels per CPU socket, which is a normal thing these days already with the Intel Silver level CPUs. You just need to make sure that you really populate all the 6 channels that come with the CPU socket. And I already mentioned that you need to keep an eye on the balance for NVMe drives versus NICs that you have in the system. So let's go through this on the example of an Intel system. Of course, everything also works with AMD here. But for an Intel single socket, what you have are 48 PCI lanes, or twice as much, 96 PCI lanes for a dual socket system. But for a dual socket system, you try to design it in a way that you don't need to cross the link between the sockets, because that would add extra latency, and the whole point of this is avoiding extra latency. So in this sense, a single 100 gigabit NIC takes up 16 PCI lanes and really needs the bandwidth of all these 16 PCI lanes. And a single NVMe drive uses 4 PCI lanes. So what this means is you want to match the 4 PCI lanes of an NVMe drive with the 16 PCI lanes of the 100 gigabit NIC for the perfect balance. That means you will have up to 4 NVMe drives per 100 gigabit NIC. Adding drives beyond that is of course possible, but typically that means you're adding more capacity and not more performance to the server. And since you want to avoid crossing the sockets and to avoid adding extra latency here, what you want to do is in a dual socket system, you want to have 2 NICs, one of them for each socket, and then up to 4 drives behind each of the sockets to get the full performance out of the system. Okay, so much for the software side. Now we're taking a closer, for the hardware side, now we're taking a closer look at the software side of things. We'll talk about NVMesh and BeeGFS here. What is NVMesh? In general, it's software-defined block storage, so it becomes the replacement for the traditional RAID controller. The one important thing in NVMesh is that it has been designed from the ground up for NVMe, so to really preserve the low latency and high IOPS of these NVMe drives over the network with the lowest possible latency, and to provide scale-out volumes, meaning highly available volumes that can scale out across multiple servers. And so far it's all block storage. Typically what your applications will want to have is a file system on top of that. So for that, BeeGFS is optimal because it has been designed at an HPC center with a strong focus on performance, and the internal architecture has really been designed to efficiently handle such lots of small files, highly concurrent access, and various system sizes scaling from very small up to very large, whatever makes sense in your environment. So what you have with both of them together is a very flexible software-defined solution that works on top of commodity hardware. Okay, let's take a closer look at the internals of NVMesh. The one important thing that I mentioned is that it has been designed especially for NVMe drives to preserve the low latency when accessing NVMe drives over the network. How does that work? Excelero has a very important patent in this area called RDDA. And on the left-hand side, what we have here is a client that wants to access an NVMe drive on the right-hand side here on the server. And let's see how this goes. What the client needs to do is, of course, to go through the network interface over the high-speed network, arrives at the network card of the server. And now comes the very important thing. If we would need to wake up a process on the CPU in the server here, then we would already add a bunch of extra latency, and we want to avoid the extra latency here, of course. So the special technology that Excelero developed for this, RDDA, stands for Remote Direct Drive Access. So it's conceptually similar to RDMA for networks. And what this means is that the NVMe drive can be accessed directly from the network card, completely bypassing the CPU. So with this mechanism, we add about 5 microseconds to go remote. And looking at the typical spec sheet of an NVMe drive, the access times there are about 100 microseconds. So with Excelero's NVMesh, going remote to an NVMe drive turns these 100 microseconds into 105 microseconds. And this overhead is so insignificant that we say Excelero's technology enables access to remote NVMe drives at the same performance that you would have if the NVMe drive would be directly inside the client. But in general, it's of course not only about accessing a single NVMe drive. What you actually want to have is protected volumes on top of the NVMe drives to have a replacement for the traditional concept of RAID controllers. So that's the other important thing that NVMesh provides. On top of the servers, what you define are the logical volumes with multipathing already built in, because as we discussed, typically you will want to have more than a single 100 gigabit NIC inside a server, which means you automatically have multipathing to the drive. And this is all handled internally by Excelero's NVMesh, so that the logical volume you want to appear at the clients only appears once, but NVMesh is internally aware of the most efficient path to a drive and can do the transparent failover to an alternative route should it become necessary. The next question is then, which kind of logical volumes can you create with NVMesh? The very simple one is what we call here the concatenation. That simply means you add the capacity of multiple drives. That's typically not very interesting for high performance. More interesting is the striping across multiple drives. That's comparable to the classic concept of a RAID 0. The important difference here is that the drives do not need to be inside a single server, because as we said, we enable the access to remote drives at the same speed that you would get if they would be inside a client already. So the drives here can be striped across multiple servers for the scale out. More interesting for high availability is the mirroring, or the combination of striping and mirroring. This would be equivalent to the classic concept of a RAID 10 volume. The important difference here is again that the drives can be inside separate servers. That means with this concept, you do not only tolerate the failures of drives, you can also tolerate the failures of complete servers while still having all the volumes and all the data available, with the ability to make it accessible anywhere on the network. The good thing about the mirroring is that on the one hand, you preserve the full read performance of all of the drives, because NVMesh spreads the requests equally across all the drives. And for the writing, it is also very efficient to preserve the high IOPS, because the only thing you need to do for mirroring is, instead of sending the request to only one drive, it needs to be sent to 2 drives. So this is very efficient. Of course, it comes with a capacity overhead, but it's the most efficient thing you can do to preserve the performance and also provide high availability. For other cases where write performance might not be as important and read performance is still very important, we're currently developing erasure coding. You could compare this to the classic concept of a RAID 6, meaning there are 2 parity drives. The difference again is that these RAID 6 volumes can be inside separate servers to again not only tolerate the failures of drives, but also the failures of complete servers. Again, you will have the full read performance of all of the drives in the system and up to 90% usable capacity compared to the mirroring. But for the writing, the mechanism, and that's in the nature of things, is less efficient, because what you need to do if you want to update a small random block on one of the drives is that you need to find a way to compute the new parity. So that means to update a single small random block on one of the drives in a volume, you first have to read the old block that should be updated and read the 2 old parity blocks. From that, you can compute the new parity, and then you can write out the new block and the 2 new parity blocks. So that means for a single small write operation, you end up with 6 operations in total. 3 of them are read operations and 3 of them are write operations. Just to say it again, this is not a design fault of NVMesh. This is just in the nature of how RAID 6 or erasure coding works. So it's a cost that you would need to pay for this, This is why most of the people actually decide to go with mirroring instead of erasure coding. But as it should be for software-defined storage, you have, of course, the full flexibility to choose what's best for you. And with that, I'm handing over to JF.
Hello, everybody. Thank you, Sven. Let me see if I can control your screen. Aha. Does it work? Wait a bit. A slide. Here we go. So hello, everybody. Thank you again, Sven, for your introduction. In fact, before starting to talk about BeeGFS, I am going to jump back in the slides for, here we go, to that one, the general architecture of an NVMesh deployment. So as Sven just explained, NVMesh is a software-defined storage that typically uses NVMe's and assembles them, cuts the available storage, mirrors it, stripes it, and provides logical volumes that appear as block devices on the servers. And that's quite an important point when it comes to how we're going to use them. So, of course, if you've got a block device, you can format it locally with a local file system. Whether that block device is in the machine or whether it's an NVMesh logical volume, it's the same. So you can format it locally, mount it locally, that's fine. That machine will have a lot of bandwidth available. If you want to share that super fast block device between various machines, then you have to go over the network one way or another. So of course, you could re-export that file system with something like NFS. But then you find yourself bottlenecked by that single machine on which you've mounted the block device and you re-export it. So very quickly, you're going to end up with more bandwidth on your NVMe side and on the NVMesh side than what you can actually provide through NFS. So if you want to go faster than that, and if you want to scale up, you will have to have a parallel file system. And a parallel file system means multiple servers mounting multiple logical NVMesh volumes and re-exporting them in a coordinated way. And that is where BeeGFS comes in. So let's jump back to the slides. So for those who don't know BeeGFS yet, I assume that some in the audience might never have heard of it. BeeGFS is a parallel file system. If you've heard of file systems such as Lustre or to some extent GPFS, which has now been renamed as Spectrum Scale, it is part of the same family of file systems. So essentially, it clusters together a large number of storage servers and pulls all the resources of those storage servers to provide both capacity in storage and bandwidth. Each storage server will have one or more network interfaces, and the global aggregated bandwidth of your BeeGFS cluster will be the sum of all your storage servers. So this slide that we have in front of us is an example of how things operate. When you're writing files to BeeGFS, the files are chunked. They're split into blocks of data of the same size, which have the numbers, which have different colors and numbers on the servers. And then the writes are spread across all the servers that are part of the cluster. So again, you have this idea of very high performance and aggregation of the capabilities of all of your servers. You can also note that in the case of BeeGFS, the metadata server is separate from the storage servers. And in fact, you can have more than one metadata server, which allows different performance tuning and different performance profiles dedicated for metadata usage, as opposed to bulk transfer for storage. And so the bottom line is, with the use of a parallel file system like BeeGFS, you aggregate the performance of your servers. If you want more performance, well, that's quite simple. Just add more servers and it's going to scale. And that's really as simple as it is. You just add new storage servers, you've got more capacity and more bandwidth. So as noted on that slide, BeeGFS is fundamentally hardware independent. It's hardware agnostic. So you can run BeeGFS with rotating drives, you can run BeeGFS with SSDs, and you can run BeeGFS with NVMe's, both locally and through a logical manager, such as a high-performance logical manager, such as NVMesh. But as Sven very correctly said, once you have enough NVMe devices, you get to a point where the standard model of storage using RAID controllers locally in the machine or using external storage plugged to the back of the servers breaks down. So it works with rotating drives, it works with SATA or SAS SSDs, but with the bandwidth of NVMe, you need something else. And that is where the combination of BeeGFS and NVMesh really shines, because you get both the capacity and the performance at the same time, and you can scale it at will. Sorry. So many sites that use BeeGFS often have some sort of tiering mechanism. So we've been talking about NVMesh. NVMesh is the very fast option. It provides logical volumes as block device. BeeGFS uses those block devices to store its data and benefits from the performance of NVMesh. But most sites will have a mix. They will have or want fast storage with redundancy, and quite often on the side they will have slower storage, typically hard drives for cold data or warm data, but not the hottest. So there you have two main options to implement that tiering. You can either go with two separate file systems, two distributed parallel file systems, both of them possibly BeeGFS, and one of them uses NVMesh and the other one uses a standard HDD or SSDs. But BeeGFS offers a feature that allows you to mix different types of storage inside the same namespace. So only one file system and one mount point. And this is called the storage pools. And within your cluster, you have your servers. Each server has a certain number of targets. And you can group those targets into storage pools. And you can say all my NVMesh targets, high performance, go into a high performance pool. And all my rotating drive RAID arrays go into a slower, presented here as a capacity pool, essentially the bulk storage in the backend. And BeeGFS provides you with tools to migrate the data between the two at will. So you can have tiering within a single namespace. Now, let's have a quick look at some of the ways that NVMesh and BeeGFS have been implemented together at some customers or partner sites. Oh, we're back to that slide, but that slide has been changed a little bit. It's almost the same as the one we saw earlier. It's the same logic. We've got the servers, including the NVMe drives. NVMesh runs on those servers with the NVMe drives, does its magic to present the logical volumes with redundancy, with striping, everything that as you want it. And then BeeGFS uses those logical volumes and provides a distributed file system that can be used on the client nodes by any application that you have running, as BeeGFS provides a POSIX API on the client side. So anything that uses that talks POSIX one way or another can use BeeGFS and benefit from that scalability and bandwidth. So one system that we've seen popping up in recent times and that a lot of people have been asking about is how to deploy, well, actually it's more of a question. How can we deploy NVIDIA enclosures, DGX or equivalent, with a bazillion GPUs inside, multiple InfiniBand links at the back, together with BeeGFS and NVMesh to have the fastest bandwidth possible, because the GPUs are extremely bandwidth hungry and they need the ability to do very, very fast I/O. So this is a very interesting system because it's a kind of an exception. Usually you have a lot more clients than servers. But here, because the clients, logically, the machines acting as BeeGFS clients are such complicated machines with so many GPUs, so many interfaces, they de facto, they behave as multiple clients inside a single box. So we can see here a typical example of how things would be deployed. We've got two NVIDIA machines connected to InfiniBand switches for low latency and bandwidth. And then those switches are all cross-connected to servers that run both NVMesh and BeeGFS. So they use the internal U2 NVMe drives, and NVMesh creates logical volumes, BeeGFS re-exports them, and the NVIDIA machines mount them and access them. And so that way you can provide enough I/O for your GPUs, which would be hard to achieve otherwise on a network file system. You might be able to get that level of bandwidth internally by pulling together all the SSDs and NVMEs that are inside the machines. But if you're looking for a network file system, you will have to go distributed and parallel. Now, if we go back to the complete other end, a much more standard deployment example, that's something that we see a lot. It's very common architecture. It is a very simple converged system. So what we call a converged system is a machine on which everything runs. As you can see here, a single 4-node 2U chassis with a few NVMe drives, and everything on the server side is contained inside that enclosure. The metadata runs there, the storage servers runs there, NVMesh runs there and accesses the drives in the box. Essentially, it's a solution in a box. You just take it, configure it as you want for your network and your fabric, plug everything in the back, and your clients can access it. So here in the example that we have on the slide, we see that we have 4 servers, each with 6 NVMe drives, 2 Intel Xeons, pretty good ones, but not the absolute crazy insane ones, because neither BeeGFS nor NVMesh do in fact require a very performant CPU. As Sven mentioned earlier, a lot of the trick comes to bypassing the CPU and avoiding load on the CPU. So you don't actually need big ones. And 2 Mellanox EDR 100 gigabit interfaces per server for a total of 8. And then this goes to the RDMA fabric, where we assume we don't have any oversubscription. And then we have 8 individual BeeGFS clients, each with 1 EDR interface, which means there's no oversubscription, and we have a perfect match between the clients and the servers. And the performance results, as shown at the bottom, are really, really good for just 4 servers inside a 2U enclosure. 600,000 metadata ops, over 1 million random 4K IOPS. That is really, really high for just an all-in-one box. And so that's where you can really see the how well NVMesh and BeeGFS interoperate and work together. You get a complete solution with very, very high performance, both in metadata and in data. So, I hear a hot microphone. So to sum it up, essentially, this is what we've been talking about ever since the beginning. By using NVMesh, you gain flexibility and redundancy across your NVMe drives, across multiple servers. By using BeeGFS on top, you use the block devices that NVMesh provides, and you make a file system out of it, a very fast, parallel, scalable file system. In both cases, NVMesh and BeeGFS, if you need more performance or capacity, just add some servers, and you can do that on the fly. So you can scale it absolutely at will. And in the case of NVMesh, you also have data protection at the block device level, built in NVMesh through mirroring or erasure coding. Neither NVMesh nor BeeGFS is tied to a specific vendor. So you don't have any lock-in. You don't have to buy a specific hardware to use those products. You can install it on your own hardware if it provides what is needed by NVMesh, which is essentially NVMe devices and a lot of bandwidth. So you don't have a lock-in. And we both have networks of partners who can work with you for your specific needs to design both a hardware solution and a software deployment on top of it to match exactly your requirements of bandwidth, latency, and capacity. And I think that, if I'm not mistaken, this wraps up this presentation. Sven, Tom?
Jeff, I was answering a question. I've been getting quite a few interesting questions. One that came from Becky, and that was one, I think it's for you, Jeff, but you guys can decide between yourselves who's going to take it. Becky was asking, what are the tools for migrating between spinning and NVMe?
So this is within BeeGFS, we have a migrate command. So, all right, you can create a directory and specify that this directory will be on a given storage pool. And then any file created within that directory will inherit that characteristic, and the data is going to go to that storage pool. But now and then, of course, you want to change that, and you have a migrate tool that allows you to take any file and migrate it. And it's really that simple. It's within the BeeGFS CTL command.
All right, cool. Another question, and questions are coming in fast. Please, people, do keep asking questions. They're great. James is asking, what does the BeeGFS metadata look like on the Converged system?
So the BeeGFS metadata is stored on a perfectly regular block device. And on the case of that Converged system with NVMesh, the block device for metadata would also be an NVMesh logical volume. And then it's stored as a directory tree and files containing the metadata.
So actually this means the metadata and the normal file contents for the storage service can be located on the same devices. With spinning disks, that would be a very bad idea because of the disk seeks that come from this. But for NVMe devices, it's not really a problem because they have no problem with disk seeks and they provide the higher IOPS anyway.
Okay, cool. Then I got a question from Peter. What about high availability that tolerates node failure? Can you configure BeeGFS with buddy groups but without mirroring?
All right, so actually there wouldn't be any point in doing that. In fact, from the point of view of the operating system, so you've got to remember, NVMesh appears as a block device, and it has a very interesting capability of that block device can appear on more than one machine, except that you've got to be really careful about how you use it. So you treat NVMesh as an external shared storage as far as HA is concerned. So you need a CoroSync and pacemaker cluster and one service that runs on a given machine. If that machine crashes, the BeeGFS service will start on another machine and access the same logical volume as the one that just crashed. So essentially, if you have if you have mirroring at the NVMe level, you definitely don't need nor want buddy mirroring at the BeeGFS level.
All right, cool. Thank you so much for that. Another question from Becky. I like it when people come back with more questions that shows attention. For migration, will you have 2 copies of the data, one on NVMe and one on hard disks?
Briefly, while the data is being copied, and then the original one's going to be removed. At the end of the day, you only have one copy that is in one of your storage pools. If you want the same data in both, you will need 2 different directories or 2 different files, one way or another.
Okay, and then 2 questions that are related to each other from Ranjan and Becky as well. So what is the price range for the 4-node storage solution shown in the slides? And Becky was asking the pricing model. I'm not expecting a full answer here, but maybe you can give some sort of an idea.
Yeah, so in general, both NVMesh and BeeGFS together are priced based on the number of servers. And then there's a price per server per year for the maintenance. The major cost of the system is actually the hardware itself. So the software, as it should be, just adds a fraction of the hardware costs on top of that.
All right, good. And we're going back to technical questions. Mike is asking, on the Converged servers, do you still need the RNIC?
Yes, because I assume this means the RDMA NIC, because you want to have the very fast mirroring or high availability between the servers. So there it absolutely makes sense to still go with an RDMA NIC. But if this was also part of the question, you will not have separate NICs for NVMesh mirroring and for BeeGFS. They will just share the same NICs.
Cool. All right. Thank you, Sven. John is asking, what about server high availability? I assume that means how do we implement an environment where servers can fail?
So this rejoins the question earlier about mirroring. So again, the block devices presented by NVMesh essentially behave as an external shared storage. So you can implement high availability by the industry standard tools. So a CoroSync cluster running pacemaker resources, and you treat your NVMesh logical volume as external shared storage. So the resource migrates from a server to another one when the first server crashes. And so NVMesh provides you with redundancy and protection at the data level, and using a pacemaker and standard HA tools, you gain, on top of it, you gain redundancy against server failures.
Maybe the other interesting thing to add here is that the system is, of course, active in that sense. That means while all servers are up and running, all of them are adding bandwidth and IOPS and sharing the data. So it's not active passive, that some servers would be idle for the time being. That's also very important for the performance, of course.
Yeah, that is indeed a very good point.
Okay, I'm gonna Peter, whose question we answered before, is now asking to put up the slide just after which hardware components are critical. So if one of you can go back to that one.
Mm-hmm.
And then his question, with erasure coding, would the CPU load slow down?
Which hardware components are critical? The one after this, you said?
Could you please just, could you put up the slide just after which hardware components are critical? Yeah, so.
This is which hardware, and this is the slide after, yes?
Yes, and I'm not sure if that relates, but then with erasure coding, would the CPU load slow down, allow higher density?
The density that we defined here is basically, maybe this rather relates to this slide, is basically defined by the speed of the network. And even with erasure coding, you have still the full read performance of all of the drives. So in that sense, higher density, yes, you can of course always add more drives to a single server to add more capacity, but it still wouldn't add more performance if you exceed the balance that we discussed of 4 NVMe drives per 100 gigabit NIC.
Right.
But higher density in terms of capacity, yes, for the mirroring, you need to have twice the capacity. And for, so that means you have 50% usable capacity given by the raw capacity. And for the erasure coding, yes, it's more dense with respect to capacity. You can have up to 90% usable capacity that would match the classic concept of a RAID 5 volume where you only have a single disk for parity then.
All right, thank you. And I got a question from Guillaume. Is the latency lower with an AMD EPYC 2 platform than on the Intel, since there is no PLX switch on the AMD and the PCIe is version 4.0?
Yes, very good question. We're still waiting for the AMD ROM systems to become generally available for testing. There are only a few samples out there that are not really NVMe optimized yet, so this remains to be proven. The old generation EPYC was in fact a bit slower than the Intel CPUs with respect to latency due to the way everything was internally wired inside the CPU. From the spec sheet and the high-level design, it looks like the AMD ROM platform would indeed be excellent for fast NVMe storage, but we were not able to validate this yet.
All right, and another question from Guillaume. For an 8-node BeeGFS cluster, is it faster to spread the metadata service on all servers or to have 2 dedicated metadata servers?
For an NVMe cluster, I would definitely say spread the metadata across all the servers, because then you can really benefit from the performance, especially in very metadata intensive situations where you might not even need all the bandwidth that would otherwise be idle on the storage servers if you would have only dedicated storage servers.
All right, and then another question from Becky. Keep them coming, Becky. How are we notified from Excelero if a drive goes bad, and how do we recover?
Perfect question, yes, and a very valid one. NVMesh comes with a very nice graphical interface on the one hand to make everything super simple, that runs in the browser and gives you the usual dashboard. I think we actually have a picture here. Yeah, so the dashboard can of course show you live statistics and shows you the green lights when everything is up and running as it should be. And it can of course also send you an email when a drive fails. So then the only thing you need to do is replace the drive by a new one, and then NVMesh will automatically integrate it, meaning this all is fully transparent from the BeeGFS perspective. BeeGFS will not even notice this because of the redundancy and the transparent failover mechanisms that are internal to NVMesh.
All right, and then I got a follow-up question from Amir on the previous server HA question. He asks, when you say 2 storage servers in HA would be active, do you mean 2 storage targets?
Actually, yes, maybe even more, because otherwise on only 2 storage targets, the ext4 and XFS file systems could again become the bottleneck for the number of IOPS that you can have from all these NVMe drives inside the servers. So typically what you will do is to create a whole bunch of logical volumes, a few small ones for the metadata, format them with ext4 as you're used to, and another bunch of larger logical volumes to take up the major part of the capacity of the drives, formatted with XFS for the high streaming bandwidth. And then you run BeeGFS in what we call multi-mode, so that you have several instances of the BeeGFS services running. Each of them has its own exclusive underlying ext4 or XFS volume to access. And that way you can even do the NUMA optimization by binding the service instances to the CPU socket, which also has the corresponding NIC and the corresponding NVMe drives behind it, so that again at the BeeGFS level you also don't need to cross the sockets to avoid adding extra latency.
All right, thank you. Follow up from Amir. Can you bind them with BeeGFS options?
Yes, yes. There is an option inside the BeeGFS metadata service and storage service files called tune bind to NUMA zone. This is exactly for that. You typically have 2 CPU sockets, so you set this option to 0 or to 1 to bind to one of the 2 available NUMA zones.
Okay, Sven, I got 4 more questions, or Sven and JF, so keep it short because we're getting towards the top of the hour. I want to give people the chance to ask maybe a few more, but let's get to those 4 first. Mike, again, he's asking, he's telling us that his current network infrastructure is built on OmniPath. OPA supports RDMA, so is NVMesh compatible with that?
NVMesh is not compatible with OmniPath, so in this sense, you might need to have a separate switch to have Mellanox-based RDMA in the backend, and then BeeGFS could run over the OmniPath, so that you could still use such a solution on an OmniPath network. Correct me if I'm wrong here, please, JF.
I guess you're not wrong.
Yes, sorry, I was on mute. This is correct.
Okay, good. Then switching to a question from Roy. How do you expand storage by adding drives? How do you expand storage by adding drives or additional servers? Does Excelero restripe or rebalance the backend data?
Yes, adding is always very simple. Like implied in the question, you can always add more drives to an existing server, and Excelero indeed can just grow the volumes, and even the XFS or ext4 file system on top of that can be grown at runtime, and BeeGFS will then just see the larger capacity from the underlying storage. So that's simple. The other thing is, of course, that you can always add more servers. Again, this can even happen at runtime without any interference.
All right, and then I got a question from Demir. Is Beyond Deploy supported, and how is redundancy handled in such case with erasure coding?
I didn't get the first part. Can you repeat that, please?
Beyond Deploy supported. So supporting Beyond, that was the first part of the question. And then in that case, how is redundancy handled with erasure coding?
You want to take that one, JF, or should I?
Well, definitely for the Beyond part, I can. So Beyond just takes block devices like BeeGFS. So you can use a logical volume from NVMesh as a target for Beyond. For erasure coding, you might want to take it, Sven.
Okay, so on the one hand, for Beyond, this also adds a new level of flexibility, of course, because based on the fact that we can access remote NVMe drives at the speed that you would have of a local drive, this opens up the possibility to either not even have the NVMe drives for Beyond inside the compute nodes like you would usually have, but instead in a separate box, or only have a few compute nodes with NVMe drives and make all of these NVMe drives or fractions of it flexibly available to the compute nodes where you want to run Beyond. So that can save a lot of costs because you don't need as many NVMe drives. For the erasure coding, the volumes will be striped across, for instance, 8+2, so 10 drives that can be inside a few or a lot of different servers. And then again, we can make these volumes flexibly available anywhere on the network, so that you can use Beyond as usual on top of that.
All right. And then James is asking, is there a benefit to having a dedicated NVMe metadata storage target, or or can metadata be stored on the same block NVMe device as the storage without a significant loss of performance?
Yeah, for the smaller systems, I would definitely recommend to just store it on the same devices. For the very large systems, or where you need to guarantee a certain quality of service or things like that, it might be useful to have dedicated servers for metadata, but typically it's absolutely okay to use the same devices.
All right. I think this is going to be the last one, unless someone is very quick. This one is again from Becky. Is there any work from BeeGFS that would allow direct access to the block devices through Excelero instead of using ext4 or XFS?
Not at that point. BeeGFS still assumes that we have a file system underneath and that we can rely on the file system to do directory management, extended attributes management, and all of that. So we do not have a file system equivalent or an object storage within the BeeGFS servers to do that right now.
All right, guys, that was amazing. So many good questions. Really love the interaction. Really love the BeeGFS, and no problem, Becky. Glad to help you out here. Very happy to see all the interaction with this community. Great session, good content. Jeff, thank you very much as a partner guest. Sven, as always, thank you very much for a great presentation. Folks, the replay of this webinar will be mailed to you probably early next week, so you can listen again if you want. Feel free to get in touch. You have my email address, and I'm sure that you know how to find Sven and JF. We will be at Supercomputing in a couple of weeks together with ThinkParQ and other partners such as Mellanox. So for those attending Supercomputing and who would like to have a live conversation, very happy to meet you guys up there. Or if you would like to have an in-depth chat about any of this, feel free to drop us a message. Always happy to set up a one-on-one call or a team call if that is necessary. With that, thank you very much everybody who attended. This was a great webinar. Have a great rest of your day or evening, and we hope to see you in a future webinar. Thank you so much.